Hi, as you can see in video number 12, I'm going to be solving question number 7 from the online sample exam P questions that you can find on the SOA's website. Before we get into solving the problem though, I'd like to share with you that my son and I had the chance to go to the Star Wars Celebration convention in Chicago this last weekend. Enjoyed seeing some panels and various exhibits and just spending time together. We even got to make a little video that I'll show you now. Here it is, as part of the Galaxy's Edge exhibit, which is going to be ultimately part of Disney World and Disneyland. We even got to do a 30-second testimonial of what Star Wars means to us. Thousands of people were able to do this, and you should look for it if you ever go to Galaxy's Edge at Disney World or Disneyland. You can give a shout out in the comments if you enjoy Star Wars or if you got a good chance to go to the Star Wars Celebration. Alright, back to the math. Before I talk about this problem, I should say that we have been talking about independent events recently. That's not going to come up in this video, but it's very important for the future, so if you haven't watched those videos, that's something to do. We'll be using independence a lot. Another thing to comment about here is the way we're going to solve this involving a Venn diagram. The way we break it down, especially with the special addition rule for mutually exclusive events, is going to be helpful very soon, maybe in the next video or two when I get into problems involving Bayes' theorem. So if you've been looking for problems involving Bayes' theorem, that's coming very soon. So yeah, we are using a Venn diagram, we are using the special addition rule for mutually exclusive events, and we're going to use the general multiplication rule, not the special one, to find a useful thing, the probability of renewal of at least one insurance policy by a randomly chosen customer. So we have an insurance company that's got information about their policyholders, their customers. 40% of the policyholders have only an auto policy covering their car or cars. 40% of them are going to renew next year. That's really, if you think about it, a conditional probability. If I know this person has only an auto policy, there's a 40% chance that they will renew. 60% of policyholders who have only a homeowner's policy will renew. That's also a conditional probability. If you know they have only homeowners, what is the probability that they renew? So those are hints that probably the general multiplication rule is going to be necessary, not the special one for independent events. The company estimates that 80% of policyholders who have both an auto policy and homeowners will renew at least one of those policies, maybe both. This would include both. Company records also show that 65% of policyholders have an auto policy, 50% have a homeowner's policy, and 15% have both. Right? Those are ordinary probabilities. Using these estimates, calculate the percentage or probability of the policyholders that will renew at least one policy next year. So if I let say R be the event that a policyholder, renews at least one policy next year, at least one, that's the event whose probability that I want to find. I want to find P of R. Okay, that's the goal. Yeah, Venn diagram's helpful, but you got to be careful in how you draw it. In this case, it's best probably not to draw two circles representing, say, auto and homeowners, or three circles, another one representing whether they renew or not. For one thing, with the auto and homeowners, those are really two events whose union is going to be the entire sample space. They don't talk about any other kind of insurance policy here. Evidently, all the customers have either an auto policy or a homeowner's policy or both this year. So instead of drawing two overlapping circles, I want to draw, say, two overlapping rectangles. Let's say this red one here, about like this, represents people who have an auto policy this year, possibly also a homeowner's. And another rectangle that has overlap, say like this, represent people who have a homeowner's policy this year, and again also possibly autos. This rectangle over here, just right there, would be those people with an auto policy only, not a homeowners. This one would represent those with homeowners only, not an auto. And the intersection would be when they have both. Should I draw R in this picture? Sure. And I could draw it as a circle that overlaps everything, but I also could just draw it as a rectangle, say like this. Say going this way, this is going to represent R, okay? And I guess that would mean this rectangle up here represents R prime. The complement of R is what I mean there. Okay, so once you've drawn the picture, what's helpful about it? And here's the thing that's helpful about it, and this is the thing that's going to be useful when we start talking about Bayes' theorem. R is, again, this rectangle down here. I can break that up into three pieces, three mutually exclusive, disjoint pieces, non-overlapping. This piece right here, this piece right here, and this piece over here. So that's a hint that maybe I want to write this as a sum of three probabilities. The probability of this, plus the probability of this, plus the probability of this. The probability of, what would this, how could you represent this part right here? How about R intersect, not A, but A intersect H prime, right? Because that's an A, but not an H. A itself would include, if I did R intersect A, that would include both of these. Plus the probability of the middle piece here, which would be R intersected with A intersect H. Like that. I'm using parentheses like this just for emphasis. I don't really need to. Plus the probability of this part here, that would be R intersected with H intersect A prime. I'll write it as A prime intersect H. So that's the special addition rule. Special addition rule for mutually exclusive events. Okay? Now remember, when I started reading this problem, we were also thinking about the fact that these numbers up here were conditional probabilities. These numbers right here are ordinary probabilities. That should set off light bulbs in your mind saying, hey, probably I need the general multiplication rule. And that's what you do. You also have intersections in here. That's another hint. So what does the general multiplication rule say? General multiplication rule, not the special one for independent events, but the general one that works all the time. It says the probability of, say, let me call them C and D. C intersect D is the unconditional probability of C times the conditional probability of D given that C has occurred. We've seen this before. C and D are interchangeable. They're symmetric here. You could also rearrange this as the probability of D times the conditional probability of C intersect D. Both of those things are true. Okay? So up here, for example, with this one, C could be played by, the role of C could be played by R, and the role of D could be played by this thing, A intersect H prime. Let's go ahead and use that here with all three of these. So, and does that make sense though? Careful here. What kind of conditional probabilities do I know up here? I need to be more careful. Well, for example, this one right here, this 40%, is what kind of conditional probability? It's the probability that they will renew given that they have only auto policy. Only auto would be A intersect H prime. That's what that is. So actually, in thinking about which of these to use, which should play the role of C and which should play the role of D, well, if this is C and this is D, thinking about what I know up here, I want, let's see here, I know the conditional probability there. I want this to be the form that I use, okay, because C is going to be played by R. So let's go ahead and use that here. So it's going to be the regular probability of A intersect H prime times the conditional probability of R given A intersect H prime. That product from the general addition rule is what this equals. But I've got three of those. For the next one, it's going to be the ordinary probability of A intersect H times the conditional probability of R given A intersect H. And the last one over here is going to be the unconditional probability of A prime intersect H times the ordinary probability, or the conditional probability of R given A prime intersect H. Okay, so those conditional probabilities up here, these four numbers are going to go in these three spots here. Careful where they go though. What about these numbers here? That can be figured out from these numbers here. We know overall that 65% of the people are in A, 50% are in H, and 15% are in this rectangle here in both. Think about that intuitively. That's going to mean, I can work backwards, 15% are in this spot here in this rectangle, leaving 65 minus 15, 50% in this rectangle, and 50 minus 15, 35% here. So the probability of A intersect H prime, for example, that's the 50%, 0.50, times this conditional probability, that's the 40% up there, times 0.40. The probability of A intersect H prime is the 15%, 0.15, times this conditional probability of R given A intersect H, that's the 80% right there. A intersect H is when they have both policies. So that's the 0.8. And finally, we have the 35% times the last conditional probability, which is the 60%. That's what we need to calculate now. 50% times 40% is 0.20. 0.15 times 0.8, that is going to be 0.12. And 0.35 times 0.6, that is going to be 0.21. 21 here. So the answer is 0.53, 53%. And that is the correct answer. That is answer D if you look online. Okay? So here's a summary of the problem again, of the solution at least. And again, you can see that I use the special addition rule and the general multiplication rule. Thanks for watching.